Okay, here we have a couple mass balances. All right, as the name implies, they measure mass of stuff. So right now they're measuring in grams. Now you'll notice that these go out to 1 decimal place or 2 decimal places. Now here's the interesting thing about scales like these and other devices that make the measurement for us. They're already telling us what the measurement is. In other words, there's no lines to read between. So when I place this 1 mole of aluminum, or approximately 1 mole of aluminum, it's been worn down a little bit over the time, and my mass balance says 27.0 grams. Okay, now there's nothing there for me to read the lines between. I can't say, well, this mass balance gives me a measurement between this, and I physically read between those measurements. No, it's just spitting out a number like a calculator would. Okay, but the difference between a calculator and what this is doing here is it stops the measurement at some point. Okay, so this saying 27.0 grams doesn't mean it's exactly 27.0 grams absolutely all the way out, 27.000000000 grams, onwards and onwards. Instead, it's saying, for all that we can tell you, this is 27.0 grams, give or take. In other words, the uncertain digit is already here. Okay, this 0.0 is your uncertain digit. Okay, and we can show that actually with one of these scales that goes out to 2 decimal places. Okay, now this guy's a little bit more sensitive, so it's got a shield on it. Even just as I lift it up and the air kind of moves across it, you can already see that the number kind of changed a little bit there. So I'm going to take this same piece of aluminum and move it over to this balance. And this tells us 27.08 or about 27.09 grams. Okay, so when this balance says 27.0 or 27.1 grams, it's trying to do some rounding. It's trying to figure out whether to call this a 0.0 or a 0.1 or a 0.2 based on what else comes after this, as best as it can measure. But it can't say for certain as many digits as it pleases. It has limitations to how it makes that measurement, just like how we have limitations in everything else. So just because something is measured by a machine doesn't mean that it's a perfect measurement and it can just go out to as many decimal places as possible and it has no uncertainty. This has definitely uncertainty as well. And since the measurement's already made for us, it's going to be the last digit. This 27.1, this 0.1 is your uncertain digit, the 10th place. Okay? When we have 2 decimal places read out, like this 0.8, or sometimes it flutters to 0.09, sorry, 0.08 or 0.09, this is going out to the 100th place. And this 100th spot is our uncertain digit, which means this could be rounding to 0.08 or 0.09 based on something else. The fact that this is kind of fluttering between those is actually a great example of how you can kind of tell, like, ooh, it's got to pick between these. It's not for sure like, oh, this is definitely 27.08 or this is definitely 27.09. The fact that it kind of is, maybe it's this, maybe it's that, means it's kind of having a tough choice between those two. Kind of like how this had to go between 27.0 and 27.1. Picking between 27.0 and 27.1 might have been a little bit tough, especially if we're floating this close to 27.1 right here. Okay, now depending on the device also, sometimes your measurements are a little bit different. So whenever you do an experiment, you want to stick with the same scale throughout. So for example, if this scale is off by 0.1 gram in its measurements, it's not perfectly calibrated, then you'll want to have the same measurements every time, so it's always off by the same measurements. Otherwise, if you go switching scales partway through, you might have one scale off by 0.1, one that's off by 0.1 in the other direction, maybe one's off by 0.2, and so you have a little bit more variation in what you use. This is also why we tend to use the same glassware for things. We make sure to zero beakers and weighing cups, weighing dishes, instead of just saying, well, this beaker is the same size, so we should use this mass, and it's the same. It can be a little bit different, even just from glassware to glassware, from scale to scale. Okay, now let's try this on one last scale that can go out a little bit farther. So I'm going to close that there. Like this. Okay. Okay, so this is one of our analytical balances. This is a really fancy balance that's used to go out to 3 decimal places. It's got these glass shields around it so we can make sure to cut down on airflow and anything moving in and out and contamination. So I'm going to open up one of these doors, place our sample in the center, like so. And what we get now here is not just 27.08 or 09, it's 27.074. So our uncertain digit in this case is this third digit right here. Again, there's nothing to read between the lines on because this is spitting out the number for us. It's already picked the uncertain digit. And as it just kind of moved from 0.074 to 0.075, you can kind of tell that it also has to make a decision on whether it calls it 0.074 or 0.075, depending on what else might be happening past this number that we aren't so sure about. So even very good balances like this have some level of uncertainty. A machine isn't perfect, okay? Or in other words, our measurements are always going to have some level of error or uncertainty to them. And typically, it's going to be the last digit that you can say without lying to yourself or to your data or to your colleagues or classmates.